All right, good morning, afternoon, evening, night, whenever it is that you're actually watching this video. So, of course, we're kind of in a little unique situation right here where you guys are going to have to try to learn on your own. Of course, I'm going to be guiding you through the notes. Now, of course, I know you don't have this note package with you right now. Unit B forms matter with a specific focus on gases. However, the PDF is up on Google Classroom. So if you can follow along with that one and use kind of blank sheets of paper or something to kind of follow along and try the examples or even make important notes to yourself as I'm talking. Or if you do have access to a printer and plenty of paper, or your parents do, or someone that you know, send them the PDF, see if you can get this printed off so you can follow along, at home as well. So our first topic that we're going to just look at is we're just going to reintroduce you to significant digits and rounding. Right now in the rest of chemistry, what we're going to be doing is going to be a lot of calculations, right? There's still going to be theory and stuff, but there's going to be a lot of calculations. So of course we need to make sure when we're expressing our answers, we pay attention to the number of significant digits and rounding. So we have right here, significant digits tell us how to round, and that's all significant digits are. But also make sure that our answer we get from a calculation problem is not more precise than the numbers we started with. Because every single time we measure something, it's limited to the accuracy of our tools. So our first one we're going to look at is addition and subtraction. We haven't really spent a lot of time on this in the past, but some forms of equations might have addition and subtraction, so that's why we're going to look at it. So when performing addition and subtraction problems, the number of significant digits are limited to how many places there are after the decimal point. Okay? So we don't look at how many numbers in total, just after the decimal. So you can measure something with extreme accuracy, like get something like 0.056 centimeters. That is really accurate. Or you can have poor accuracy of 2.3 centimeters. So obviously when we look at our 2.3, this one isn't as accurate because we don't have as many decimal points. So there's more error in that measurement. So to compensate like this, our final answer cannot have more decimal points than our lowest one here. So when we look at our examples, if we add two of these measurements together from our examples up here, we're going to get an answer of 3.4 because only one spot after the decimal, right? Because of this one right here, our 2.3. Or even a different example, if we add 25.121 kilometers to 10.11 kilometers, we only have two spots after decimal in our 10.11, so our final answer of 25.23 also have two spots after the decimal. All right, so we have practice right here. Like in our first one, I'm just going to go with you and then ask you to pause to go through. We got 12.2, so one spot after the decimal, right? So we got one spot after decimal. We got 15.44, we got two spots after the decimal. Obviously, one is our lower number, so our final answer should only have one spot after the decimal. So when we add our 12.2 to 15.44, we get an answer of 27.64 centimeters. Now, if you gave this answer, this would be wrong because we need one place after the decimal due to this one right here, 1. So we will then pay attention to rounding. So we have a number lower than 5 here, so 6 does not round up, it stays the same. So our final answer is 27.6 centimeters. So you will notice that I'm going to write the units as well because units matter. So when you're expressing your final answers, you need to make sure that they have correct number of significant digits and of course the units, because I need to know what we're being measured in. Because 27.6 centimeters is completely different than 27.6 millimeters, 27.6 inches, 27.6 kilometers. Okay? So pause the video and the answers are going to go up in 3 seconds. All right, so 3, 2, 1. Boom, and here are the answers. So you will notice that every single one does have the correct number of significant digits, and I did highlight here on which rule we used or which one kind of guided how many significant digits we needed. And you will notice I have my answers, correct number of significant digits, and of course the units. All right, so let's look at the next one. Next one's multiplication and division. Now, most of our equations that we are going to have will use multiplication and division. So these rules are kind of the main ones that we're going to follow. Now, this one right here, we have to make sure our answer cannot be more precise than our least precise measurement. So that means the lowest number of significant digits inside of our equation. So if that's the case, we need to be able to count significant digits in order to figure out which one has the lowest. So we have our little rules right here to determine which numbers are significant and which ones aren't. All right. So first rule, all numbers will be significant except for leading zeros. So leading zeros, an example of leading zeros, if you had like 0.00001. Okay. All these zeros right here, sorry for the Christmas colors, these are leading zeros. So these are not significant, okay? So if you see nothing but zeros leading up before your first non-zero number, then they're not significant. However, if we look at number 2 here, if there are zeros between numbers, so basically if we have a zero sandwich, then the zeros will be considered significant. So in this example, we have 1, 2, 3, 4 zero sandwich in between two non-zero numbers of 1 and 2. So that means this one, this one, this one, this one, this one, and this one are all significant, or we have 6 significant digits. And finally, we are going to, just for our sakes or simplicity's sakes, all trailing zeros are going to be considered significant. So for example, if you have 100, we're going to assume that it is an absolute value. So we have 3 digits, so 3 significant digits. So our first example, same thing. When we start going through and counting on which ones are which, you have to look at these rules here just to make sure. We have first one 1.01. Obviously, we don't have any leading zeros. We're looking at number 2. We have zeros in between numbers. Therefore, this one, and this one are all significant. So we have 3 significant digits. So I'm just going to shorthand significant digits to sig digs, just so it's easier to write out than significant digits every single time. All right. Example 2, we have 2 non-zero numbers, so we got 2 significant digits, and so on. So the answers are going to show up in a few seconds. I will do the countdown again, but please pause the video and try all these on your own. So the answers are coming up in 3, 2, 1. And here they are. So just double check, make sure you were getting the right answers here. And if you never got them, please go back and have a look through just to make sure you're doing your counting right, because this is going to be very important for when we actually get into our calculations. And speaking of calculations, our next step, so practice 2, we are going to be dividing and multiplying using these ideas of significant digits. All right. So our first example right here, 1, we have 5.50, which has 3 significant digits, and 3.2, which has 2 significant digits. So this one has the lowest number of significant digits, therefore our answer should also have 2. So when we actually put this into our calculator, right, so we got 5.50 divided by 3.2, we get an answer of 1.71875. Now, obviously, this has way too many significant digits. We need 2 because of this right here. So we will need to round. So I'm going to start counting 1.7. That's it. That's 2 significant digits right there. And because the next digit right here is just 1, right, it's lower than 5, so 7 doesn't round up, it stays at 7. So our answer is 1.7. All right. Same thing when we go down our next one. I just will do it a different color here just so we don't get confused. 25.5, right, so this has 3 significant digits. And 0.56, this is a leading zero, so this only has 2 significant digits. So same thing with this right here. Our final answer should have 2 significant digits. So when we put this into our calculator, we have an answer of something, just let me hold on right here, so 13.26. Now this has 4 significant digits, we need 2. Therefore, I'm going to do my rounding, so I can tell 2 significant digits here is my 13. Now, I look at, do I need to round this 3? No, because this is below 5, so it just stays at 13, and that's my 2 significant digits. All right, so pause the video, try the other ones, because the answer is going to come up in 3, 2, 1. And these are the answers. So just check on what you have right there. Now, I do want to bring your attention to the last one right here, 7. So when you put this in your calculator, I know you get 10, okay? But when we look at what we have here, we have 4 significant digits and we have 3, so our final answer needs to have 3. If you just wrote 10, 1, 0, that's 2 significant digits. So we're going to add 1 by writing 10.0. So this is 3 significant digits. All right, so you can have that ability where you can add 0.000 or whatever to kind of make up significant digits that's there. All right, so that's where you just have to be careful with the significant digits. Okay, so it's not always what shows up in your calculator that's the number that you're going to write down. Always go back and double check and make sure you're writing or expressing it in the proper way. All right, now our next little thing, scientific notation. So this is going to be something that you guys are going to use if your answer is either too big or too small. Now, this is referred to as a standard form or standard index form in a way of expressing numbers that are either too big or too small to be conveniently rounded to the correct number of significant digits. So basically, you're only going to use this if you got a massive number or a really small number and you can't really round it to the correct number of significant digits, okay? So scientific notation is just a way that scientists can handle very large numbers or very small numbers. For example, instead of writing a number like this, so we can notice that this is really small, right? And of course, writing out all those zeros, like if you forget one, your answer is going to be completely off. So instead of writing something like this, a scientist write 5.6 times 10 to the power of -5. When you put this, or sorry, -9. So when you put this in your calculator, it will spit this number out, but this is more convenient to read. So how does this work? We can think of 5.6 times 10 to the power of -9 as a product of two numbers, one being 5.6, that's the digit term, and the other one, the 10 to the power of -9, that's the exponential term. So this is how many, or how the decimal, in this case here, move backwards, right? 9 places, negative going backwards or to the left. So, for example, scientific notation, we have something like this. Now, just remember that even if you have a number that doesn't have a decimal, like here, a decimal is right here. Now, when we look at how many times this decimal has to move to get in between that 2 and the 4, we go 1, 2, 3, 4 times to the right, so therefore to the power of 4. Saying this right here, the decimal is at the end. It has to move 1, 2, 3 spots to get between 7 and 3 to the power of 3. Here, 2 spots. Now, you can do this, so 8.9 times 10 to the power of 1, it's not usually done, and if you do have your base number, 1.5, no change, right? So this, you'll notice if it moves to the left, or so, yeah, move to the left, right? We have a positive exponent. And here we'll notice that we're moving to the right. So if we move one spot to the right, it's a -1. If we move 2 spots to the right, it's -2. So if we move to the right, negative exponent. And it just comes with being careful, looking at it, and of course counting how many spots you're actually moving. All right, and we have this kind of summarized right here for you to read. All right. Now let's look at some of our examples. We have right here, so example, if we take a really large numbers like 466 and then multiply by this, it's, what is this, 100,000, we get this number. Now, writing this number down, once again, is way too many zeros, right? So, and then of course, this, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 significant digits. Way too much considering how we only need 3 significant digits from 466. So therefore, we move this decimal place. It moves backwards, or moves to the left, sorry. 1, 2, 3, 4, 5, 6, 7 places. I know that's kind of hard to see. It's a little jumbled there. But it is moving 7 places, right? So you can count on your own. So therefore, we write our answer, 4.66, 3 significant digits, times 10 to the power of -7. All right? In example 2, what we have right here, we got 0.10, so 2 significant digits multiplied by 0.0057. Or, sorry, 53. Apparently I can't count. So then we get our answer, 0.00053. Now, once again, this number is a little too small, and there's like 3 leading zeros there. So we move that decimal place back 1, 2, 3, 4 places to stick it in between the 5 and the 3, and we got 5.3 times 10 to the power of -4, because we moved it 4 spots to the right. Now, same thing. Scientific notation, we are going to convert all these here to scientific notation with 3 significant digits. So even though we have 200, that still has 3 significant digits. This is just practice for doing our thing. So if our decimal's at the end and we have to move it 2 places to get in between a 2 and a 0, we got 2.00 times 10, because we're moving it left, to the power of positive 2. All right? Now, our next one, when we look at it, our decimal's here. We only need to move our decimal 1 place, right? So we got 2.4. Now, we are going to have to round this to 7, right? Because that 6 rounds out to a 7 times 10 to the power 1. Now, remember, it said in the notes we don't normally do this, but this is just practice, because you could have easily wrote down 24.7, same thing. All right? This right here is a little bigger, so we have to move our decimal spot 1, 2, 3, 4 places. So 3 significant digits, 1.00 times 10 to the 4. Okay, so that's the first 3. I want you guys to pause the video and, of course, work through the other ones. And the answers are going to go up in, of course, 3, 2, 1. And ta-da, here are all the answers. So you will notice I went back as well and put in units, because as I mentioned before, we have to pay attention to significant digits and units. All right, so I did kind of go and put them back in. Now, I know a lot of these units are going to be very unfamiliar, like our kJ, kilojoules, or mmHg, millimeters of mercury, or ATM, it's atmospheres, kPa is kilopascals. So we will learn all these units eventually, but the thing is that if we know that a unit is there, let's try to put it in, all right? So anyway, these are all the answers here. So if you want to, pause the video and double check just to make sure you get them. Notice I did round when I needed to and stuff like that. Now, for problem 2, what we're going to do is we are going to solve the proper ones right here for correct number of significant digits and proper scientific notation. So this is more typical of what you can possibly get, all right? So for example, when we look at our first one right here, so number 1, we have 0.0056 multiplied by 0.00234. All right. Now, for significant digits, I am going to put this in here first. So we got leading zeros, so they don't count. We got 2 significant digits here. Leading zeros, we got 3 significant digits here. So our answer is going to be in 2 significant digits. So I'm going to do an unrounded one first. So when we multiply these together, we get 0.000131004. So obviously, I cannot leave this as it is because I don't have the correct number of significant digits. And of course, just look at all those leading zeros, right? It's just too much. So we are going to move the decimal point back 1, 2, 3, 4, 5 places. And so my answer now, I'm going to have 1.3, 2 significant digits, times 10 to the power of -5. Because I moved it back. So there's my 2 significant digits and how many spots I moved it back. All right, so we have a few more here. So 5 more. I want you guys to pause this video and try on your own, and the answers are going to go up in 3 seconds. And here we go. These are the answers. So you'll notice I did the unrounded ones, and then of course I put in the correct ones afterwards with correct number of significant digits. And there are no units here, so I don't need to worry about that. All right. Now, of course, if you're not sure on how I get any of these, please let me know. Email me right away, and we can have a one-on-one Google Chat discussion or something like that using some form of medium to contact each other to go over these here. Now, the last thing that we are going to do, or look at that, is something called dimensional analysis. And this is just kind of applying all this together to kind of make one cohesive answer, because sometimes you are going to get answers where they are different units, and of course it's like kind of adding meters and kilometers together. You can't really do it. So what dimension analysis is just a form to ensure that our final answer of a calculation has the desired units. That's kind of it. It's kind of a conversion factor, all right? So a conversion factor is just a ratio that relates the same quantity but in different units. So for example, we know 1 dozen equals 12, That is one thing. So you go get a dozen eggs, you have 12, right? And that's your conversion factor because you know 1 dozen equals 12 and whatever it is. Same thing, a conversion factor could be 1 kilometer we know is 1,000 meters. So we can use this as a conversion factor because technically this ratio sign is a, or that equal sign is a ratio, right? Because we can go 1 dozen ratio sign is equal to 12. We can have 1, oh, that's an ugly looking 1 km. So even here, right, we can say 1 kilometer ratio 1,000 meters. All right. Now, method 1 we're going to be looking at is as long as you have any units that have 2 different units in it or anything that has 2 different units in it, we can use this as a conversion factor. So for example, let's look at our molar mass. Our molar mass of units is grams per mole. And we know our formula here, but this is kind of the main thing right here is that we know we can relate grams and moles together. So we're just going to be looking at 2 different methods here, one dimensional analysis and one the traditional way of using formulas. You are going to pick the way that you like, and that's what you are going to use to solve questions. Now, dimensional analysis is extremely handy, and I would recommend trying to use it, but if you just want to use formulas, that also works. So when we look at question number 1, using formulas. If I had to give you this question to determine the number of moles of copper atoms in a 50-gram sample of copper, we would have to rearrange our equation, plug in our values, and solve. All right? Because we know if we rearrange this equation right here, we have number of moles is equal to mass over our molar mass. So if we have 50.0 grams of copper, and the molar mass for copper, if we were on it, is 63.55 grams per mole, we would get some sort of answer, which is 50.0 divided by 63.55, and we get an answer of 0.787 moles. So also from what we just learned, this is our answer in 3 significant digits. Now, that is kind of traditionally of what we have learned in the past. Now, using dimensional analysis, basically we're going to use this, the molar mass, because we relate grams and moles together. We're going to relate this as a conversion factor. And this way we can actually cancel stuff out if we want to. Just hold on 1 second. I'm just going to move ahead, see if there's room. Nope. Okay. Just here, so if we have the exact same type of question, where we have determined number of moles in 50 grams of copper. So if we have our known, which was 50.0 grams, and we're going to multiply by a conversion factor. So our conversion factor is just a fraction or a ratio, all right? So use a conversion factor so that the original units, grams, cancel. Now just remember, in order for something to cancel when we have fractions, if something shows up in the numerator and the exact same thing is in the denominator, so grams, it's going to cancel. And the unit that we want, or the unit we desire, should be up on top, so it carries through and shows up in the numerator. Now, when we look at our units here, we got moles over grams, but when we look up a molar mass where it's grams per mole, that's 63.55 grams per every 1 mole. That's kind of how we use this conversion factor, relating 63.55 grams, same thing, is equal to 1 mole, or the ratio is 1 mole. So if we do this, we will notice that by fractions, right, we have 50.0 grams in the numerator, we have grams in the denominator, our grams unit cancel out. The only unit we have left, or is untouched, is this mole. So we do this. Oh, that should be, this is equal to, and we get our exact same answer, 0.787, and now our unit of moles, which remains untouched, gets brought over and is at the end. Mole. Sorry, I'm going to put that in green. And the grams cancel out. So that is how we kind of set up a conversion factor, where the units we want to have cancel go on the bottom, the units that we want shows up on top. So of course, because we're going to be dealing with pressure, and because this is the gas unit, so pressure is just a force per unit area. The SI unit that we normally use is kilopascal, so kPa. There are a bunch of other ones, so you can atmospheres, which have ATM, millimeters of mercury, mmHg, so mm is millimeters, Hg is mercury, and a torricelli or a torr. This one isn't really standard, but it's still used. So we have our little chart here of different units, and basically what we have right here is what they're equal to. So these right here, because we have 1 atmosphere is equal to 101.325 kPa, these are our conversion factors that we're going to use. All right. So first one, I'm going to do the first two and kind of let you guys work on the other conversion factors here. So this is how you always set them up. First, you write out your given. In this case right here, our first problem, convert 2.85 kilometers to meters. So our given is 2.85 kilometers. So our conversion factor, we are going to convert kilometers into meters. So down below, if we know 1 kilometer is equal to 1,000 meters, and that was on the previous page, we're going to use these two numbers for our conversion factor. So the unit that we want to cancel always shows up in the bottom. So that means 1 kilometer shows up in the denominator. The unit that we desire, so we're converting it to meters, that means meters go in our numerator, and the number attached to that was 1,000 meters. So of course, if we multiply these here, numerator and denominator cancel out, and what we're left with is our answer of 2,850 meters. Now, obviously, this won't be the correct answer because, well, significant digits, right? We have 1, 2, 3, 4 significant digits here. We only have 3 significant digits, so I do need to convert back to 2.85 times 10 to the 3 meters. And that is my answer. Okay? So, what I want you guys to do, of course, is try some of these here on your own. Even I know we haven't really went over millimeters or atmospheres and millimeters of mercury, right? We have atmospheres and millimeters of mercury right here, so that is the conversion factor. So see if you can take the way how we did number 1 and use the other ones. And just an FYI, when you get down to this one right here, you may need more than 1 conversion factor for that one, okay? But I'll kind of go over that one in a bit. So I'm going to put the answers up, so please work on your own. I'll put the answers up in 3 seconds. All right, so these are the answers just how they look. So if you just want to double check on your own, please pause this video right now because I'm going to go over to a fresh sheet and show you this one I have highlighted. So converting the 103 or 130.4 kPa to torr because there's multiple conversion factors. Okay, so with, of course, that one right there that I just highlighted, when we write out our given, so we had 130.4 kPa. Now, when we looked up top there, there wasn't one relating kPa to torr. However, we could have converted kPa to atmospheres, so we know that there was 1 atmosphere and there was 101.325 kPa. Now, if we did this, of course, our final answer is going to be in atmospheres now. So then we needed to get rid of the atmospheres. All right, so I'll just kind of cross those out, if this will let me. All right, so our kPa's would have left out, and then we're left with atmospheres. So to get rid of our atmospheres, then we would have needed to go down the line, and of course, we convert 760 millimeters of mercury is equal to 1 atmosphere. And this way, our atmospheres can cancel out. However, then we're left with millimeters of mercury, but luckily we had 1 torr is equal to 1 millimeter of mercury. Now, because they're just ones, right, you didn't really need to show this step, but it is handy. So we will notice by going through all those steps, we would have ended up getting our answer of 978.080 torr, which equals to our 978.1 torr with our 4 significant digits. All right, so that's the big one where you can use multiple conversion factors. All right, so I know this first video is a little long, but it's just kind of getting you up to speed on a lot of things that we need. And the last thing I'm just going to talk about here is the SI prefixes. So you've definitely seen these before. So SI just stands for Standard International, which is just a method of communication used by international scientists. So we use these for really big or really small units. Now, we've already looked at using scientific notation. God, I forgot the name there. So we already looked at that. Now, another way is just giving it different units. Now, you've definitely seen some of these before. Now, I know it's not written here, but right down the middle, so right between kilo and milli, that's 10 to the 0, which is our base unit. So a base unit is just something that doesn't have anything in front. So if you think a meter, right, that's a base unit. A kilometer or a kilometer has km, or that k in front, meaning that's 1,000. A milli, right, same thing, has that prefix in front, meaning that it's a different, just using different prefixes, okay? Now, for all the ones given here, the prefix units be changed in size by multiples of 1,000. So this way, when you look at 1,000 has 3 zeros, right? So when we look at our base unit, it's 10 to the 0. Go up 1 unit to kilo, it's 10 to the 3 or 1,000. Then we go up another one, so 10 to the 6, or 1,000 times 1,000 is a million. Then we go up again to giga, same thing, 1,000 times 1,000 times 1,000, and so on like that. And same when you go down, you're getting smaller, or you divide by 1,000. So when we go up, we multiply by 10 to the 3 or 1,000, and when we go down, we divide. Now, how this will work, we're still going to use conversion factors in order to get it, because basically we're going to make sure everything is close to our base unit as possible. Okay? So when we're converting grams into a more convenient unit, basically it's just, all right, we don't want to say 1 million grams, so we can definitely use scientific notation. Or we can say, well, if we have 1 million grams, and, well, if I look at my SI prefixes, right, I convert to kilo, or maybe mega, because mega is 10 to the 6. That seems relatively big. So if I know that there is 10 to the 6 grams in every 1 megagram, so that's how this works. So what we have right here is how many of our base units in there. We can get our units of grams to cancel out, and what we are left with then is our 1 million grams is actually equal to 1 megagram. Cool, that's a more convenient unit, or 1,000 kilograms if you did that one. Same thing, converting this extremely small number into another convenient one. So you can use either micro or nano, for example. I'd probably lean towards nano and see where that gets us, but if we write our original 0.00000000001 mole, right, our conversion factor, so we want to get rid of mole. So if I use, there's 10 to negative 9 normal moles in every 1 nanomole, right? So our units of moles will cancel out. We're going to be left with nanomole, and of course the answer is, and we get 0.1 nanomole. All right, so of course you can do this with a bunch of other ways, just trying to get it, but the big thing is just kind of making sure you use your conversion factors correctly. Another way you can always realize, like, as you go down one step or another, you just divide by 1,000 and keep going or go up. Now, of course, there is practice right here. Okay, so same thing as before. I want you guys pause the video, give it a go, because the answers are going to go up in a few seconds. And we have our answers here as well. All right, so hopefully this kind of hammered out some issues that you might have had as we go through. Now, obviously, we are going to get lots of practice with significant digits and everything like that as we get going, but please make sure to review it. I want you to get or hop on Google Classroom, look at the CYU booklet, and of course section 2, where it is conversion factors and significant digits. I want you to, do what you can. If you have paper or whatever, try those. And then of course the answer keys are up online as well. You can answer those. And at some point we'll look at having a live stream where you guys can log on and I can answer your questions and go over stuff kind of using the board here, so you can actually see me work out some of the problems. Okay, see you guys for your next lesson.